Right, so this is the problem that is due tomorrow. And I'm just going to walk you. Sometimes I want to put different numbers in, but this is kind of this is the granddaddy of all problems. We got a block on a ramp with an angle, and there's friction, and we can't do much more. I mean, we could add ropes and pulleys in there, whatever, but this is kind of got everything wrapped up in it. So we're just going to do this problem together. So let's get started. All right. So close that ad, and it's a, what do we got? It's a 10 kilogram block. So we'll start just by drawing it, right? We got a block, and it's 10 kilograms. So the first step is just to draw it out so you know what's going on. It's at an angle of 45 degrees. And what we want to know is if this will slide, and if it will slide, what will the acceleration be when it starts sliding, right? All right, so there's multiple steps to this problem. The first step is simply to figure out the vertical force of gravity on this block, okay? So that's step one. Figure out the vertical force of gravity on the block, and we're just going to call that F sub g. And we know that there's another ad that popped up. We know that the force of gravity equals what? The force of gravity equals the mass of an object times the acceleration, I'm going to put gravity there, times the acceleration of gravity. So it's going to equal the mass of our object, 10, times the acceleration due to gravity, 9.8181 meters per second. So the force of gravity on this block, like it has been for the last 2 or 3 problems, which, I swear, is 98.1. I'm using this free whiteboard software, so whatever. So now we know the force of gravity on this block, right? So that's good, but the force of gravity is pulling straight down and it's on an angle. So that means that it's going to have part of the force is going to be pulling it into the block, right? Part of the force is the force between the pressing between these two surfaces. And then part of the gravity force is going to be trying to make it slide down, right? So I'm going to just be a little loose here and call this one the normal force, even though we know the normal force is actually the force that the force of gravity on the ramp is the one going down, and the normal force is actually the one going up, the ramp pushing back up on the block. But we're just going to call it that for now. And then the other force is the force of the sliding, which is going to be this part of it right there. And what we're doing is decomposing the gravity force into 2 components. And in this instance, so what we're doing is we're saying, well, our system is actually going to be, our system is actually going to be like this. So that's going to be like X and Y if you want to think that way. And so that's a right triangle. And that makes the force of gravity the hypotenuse, which means that we can solve for things like that. So that angle there is going to be the same as the other one. That's good, as the one down at the bottom of the ramp. That's going to be 45 degrees also. All right, so that's step 1. We figured out the force of gravity on the ramp. Step 2 is we're breaking that force up into the normal force, which is the force perpendicular to the surface of the ramp, the surface on which the object sets. That's the force between the object and the surface. And then the force, the component of the gravity force that's actually trying to slide this thing down the ramp. So we're going to break it up into those two forces. So now we just have to use a little trig to figure out what those forces are. So the normal force, that's the one, remember, I'll write it here. Remember SOHCAHTOA, right? TOA. So the normal force is the leg that is adjacent to the angle. So the F sub n, the normal force leg of this right triangle, is the one touching the 45-degree angle. So that's adjacent. So that's going to be cosine, right? So we can say the normal force is going to be equal to the force of gravity times the cosine of the angle. So it's going to equal to the force of gravity, which is 98.1 newtons. We already figured that out. Times the cosine of 45 degrees. So that equals, got to get the calculator out. Wouldn't necessarily have to if you've got a good handle on the unit circle, but let's just use the calculator. Times the cosine of 45 degrees. Remember to always make sure your calculator is in degrees or radians as appropriate to what you're doing. So that is going to equal 69.4 newtons. So the normal force is 69.36 blah, 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 newtons. So now that's the normal force, and now we've got to figure out the force of the sliding. So let's do that. We'll call that right, put that right under there, the force of the sliding equals the force of gravity. And now it's the opposite leg, right? So that's the O opposite in SOHCAHTOA. So that is going to be the sine of the angle. So that's going to be 98.1 times the sine of 45 degrees. And you people who are up on your trig are already ahead of me probably, but we're just going to run it through the calculator. 98.1 times the sine of 45. And lo and behold, it's exactly the same thing. Because 45-degree angle is halfway between 0 and 90. So the force in this particular instance gets split exactly between the two. All right, so there's kind of step two. Step one, we figure out the force of gravity just pulling down. Now we have broken that force of gravity up into the amount that's pressing the two objects together. That's perpendicular to the surface of the ramp. And the part that's trying to pull that thing down the ramp. And of course, the steeper the ramp, the more force is dedicated to pulling it down the ramp, and the less force is dedicated to pressing the block and the surface of the ramp together, right? Okay, so our question still is, will this thing slide? And if it will slide, how fast will it slide? So what's the next thing we need to do? Okay, I'm going to write, now that we know it, I like to write things up where they go. So now that we know it, we know the force trying to slide this thing down the ramp is 69.4 newtons. Okay? So there's that. Now we need to find what? We need to find another color, and I have blue. Blue will work. So now we need to find the force of friction holding this back. And our first question is going to involve the force of static friction to determine whether or not our force of sliding down the ramp is going to overcome the force of static friction, right? So we from the problem, we have our force of static, the coefficient, excuse me, of static friction is 0.80, and the coefficient of kinetic friction, which we may or may not need, depending on whether it starts moving, is 0.60. All right? So, I do not know what this is doing there, so I'm going to erase it. I thought I was going to erase it. I guess I don't know how this board works. Or maybe I can't erase it once I pay the subscription. Who cares? So we're going to move on. So we know the force trying to push it down. Now we need the force of static friction trying to keep it in place. And then if the static friction is great, the maximum static friction is greater than the force trying to pull it down, it'll stay in place. If the force trying to pull it down is greater than the force of static friction, it'll start to move, and then we'll have to use the force of kinetic friction to figure that out. So we have to figure out the force of static friction. All right? So do I have my blue color? Okay, I do. So the force of, and we'll write this here, static friction is going to equal the normal force, which is the force of the block and the ramp pressing on each other. So it's how hard they're pressing on each other, right? So that's going to be the normal force perpendicular to the ramp times the coefficient of static friction, whatever it is. In this case, it's 0.8. So we got a normal force of 69.4 newtons and a coefficient of static friction of 0.80. So this is going to give us the force of static friction. So the force of static friction, 69.4 times 0.8 equals 55.2 newtons. So we've got a static friction force of 55.2 newtons and a sliding force trying to push it down of 69.4 newtons. So what we see here then is the force of sliding. This is what you have to compare. You have to compare the force of the sliding to the force of the static friction. And if the force, this is the maximum, when we calculate that, we're always calculating the maximum. So I'm just going to write that up there so you know. So we're looking at the force of the static friction, sliding, excuse me. That's why I have to start writing words underneath there instead of just letters, because sometimes I get confused. So we're talking about the force of the sliding versus the force of the static friction. Which one is greater? And if we look at it, we have the force of the sliding is 69.4, and the force of the static friction is 55.2. The force of the sliding is greater than the force of the static friction. Therefore, this thing will start sliding. But what happens the moment it starts sliding? The moment it starts sliding, we can't use static friction anymore. We can't use the coefficient of static friction anymore. So now we have to use the coefficient of kinetic friction, because that's the friction of something actually moving. I'm going to trace that over in purple so I can color code everything. There we go. So now we have to use the coefficient of kinetic friction to figure out the force resisting the motion once this thing is moving. Okay? And we're just about done with this problem, believe it or not. So now, how do we figure out the force of kinetic, meaning moving, kinetic friction? Well, just like the force of static friction, we're going to take that normal force. how hard the block and the surface of the ramp are pressing together. That's the normal force. And we're going to multiply it by the coefficient, only this time it's going to be the coefficient of kinetic friction. So then we're going to get our normal force is 69.4. And now we've got our coefficient of kinetic friction, which is 0.60. So now we have our force of kinetic friction is going to be 69.4 times 0.6 equals, so our force of kinetic friction is going to be 41.6 newtons. 6.4 if you want to use that other decimal, I don't care, whatever. So we're not quite there yet. We know it's sliding. We figured that out. We figured out the force of kinetic friction. So that's going to be kinetic friction, and I'm using the purple. So that's going to be 41.6 newtons. Trying to keep it from sliding. So we have to figure out the net force. And I think at this point, we're going to switch to black because we're just about done. So the net force on this thing, because remember the net force is what determines the acceleration, is going to be the force of the sliding minus the force of the kinetic friction. All right? So how much is trying to pull it down, the gravity trying to pull it down, minus the force of the kinetic friction trying to keep it from getting pulled down. So that's going to give us 69.4 minus 41.6. And we are very near the end of this problem now. 69.4 minus 41.6 equals, so our net force, trying to slide this thing down, taking account for friction, because we don't live in a frictionless world, so we don't have to pretend any longer. It's really nice not to have to pretend. So we're going to have a net force of 27.8 newtons trying to slide this block down the ramp. And to top it all off, now we're trying to figure out, remember, if it slides, how fast is it going to slide? How fast is it going to accelerate? Because it has an unbalanced force on it, right? So we just go back to Newton's second law, F equals ma, right? Except we want acceleration, so we're going to say F over m equals a. And once we say that, we can say the force, 27.8, divided by the mass, 10, will give us an acceleration of, there should be like a drum roll, 2.78 meters per second squared. And we'll put that in a box, because that's what we do with our answers. All right, so that's the whole problem. Wow, that looks like a lot on the, but when you know, each little piece doesn't seem like so much. And then when I stand back and look out on the board, I'm like, wow, that's quite a bit. But you know what? It's not so bad if you just walk through it slowly like this and do it. It's going to be just fine. So there it is. I will see you in class on October 28th. And if you're watching this after that, I will have seen you in class on October 28th, unless you found this video somehow else, in which case I wish you great success in solving ramp problems, including friction.